start recording. Okay. Welcome, everyone. I'm very sorry for slow delay. It was completely my fault. I confused time, 4 o'clock or 3 o'clock. And it's our last ZAG seminar this year. And Merry Christmas to everyone and Happy New Year to everyone. And it's my big pleasure to introduce our last speaker this year, Jingjun Han from Johns Hopkins University, my alma mater. I'm very happy to introduce him. And Jingjun will speak about ascending chain condition for local volumes and boundedness of singularities. Thank you.
Okay, thanks a lot for the invitation. And since it is the last ZAG seminar this year, so I think it's time for all of us to thank the organizers and hosts for your very nice organization, and especially to provide a platform for all of us in this very special year. And today I will talk about the ACC for local volumes, the boundedness of singularities. So this is a joint work with Yuchen Liu and Lu Qi. So first, let's recall some very basic definitions. Comes from singularities. So let delta be a pair, which means that X plus delta is an Arcadian divisor. And for any prime divisor E over X, then we can define the log discrepancy. So which is defined by Ky minus the pullback of Kx plus delta. I compute the multiplicity along E and plus 1. So for a pair X delta, we call it has KLT singularities or epsilon log canonical singularities if the log discrepancy is larger than 0 or is larger than or equal to epsilon for any prime divisor E over X. And if we have PLT singularities or terminal singularity, if the log discrepancy is larger than 0 or with respectively is larger than 1 for any external divisor E over X. And indeed, we can extend the definition of the log discrepancy from the divisorial valuation E to all valuation V on X. And so such kind of valuation, the center on X is a close point, small x. So this is defined in a paper of Johnson and Mustata. So now let's fix our variety, the dimension of our variety X to be n, and let X delta be a KLT singularity, and V evaluation, the center on X is a small close point X. Then by work of Lagerfeld Mustata, we can define the volume of such kind of valuation V. So the volume is defined by the limit of this guy. So you can see that the definition is very similar to the definition of the global volume. So especially the denominator, they are the same. And in a recent work of Chi, in order to establish a local K-stability theory, he introduced the local volumes and also the normalized volume of valuation V. So first, let's define the so-called the normalized volume of the valuation V. So it is defined by the S power of the log discrepancy of V multiplied with the volume of V. So the partial reason why we call this function is the normalized volume of my valuation V is that the value of the normalized volume of V is the same as the value of the normalized volume of lambda V for any positive real number lambda. So this partially justifies the name, the normalized volume of my valuation V. And now we can define the local volume of a KLT singularity. It is defined by the infimum of all the possible normal volume of a valuation V, which the center on X is at my closed point X. And by the work of Bloom, we know that indeed the infimum is a minimum, which means that there always exists a valuation V and whose normal volume of function of V could compute the local volume of my QRT singularity X delta. And by a very recent work of Xu and Zhuang, we know that the minimum is achieved by a unique valuation V up to rescaling. So for such kind of valuation V, we call it a volume minimizer of my QRT singularity. So this is about the definition of local volume. And maybe at the first glance, you can see that this definition is a little bit complicated. And we need, in order to compute the local volume, we need to consider all the possible valuation and compute the infimum. So maybe it is not so easy to compute the local volume of a QRT singularity. And if you are familiar with bidimensional geometry, so there is another concept which is called the PLT blow-up. And we will see later that indeed, in order to compute a local volume of a QRT singularity, we only need to consider a special kind of valuation or divisor valuation, which is called Kohler component. So before that, we need to define what's the meaning of PLT blow-up and also the so-called delta-plt blow-up. Again, I let my X delta be a QRT singularity, and I call a projective bidimensional morphism mu from a normal variety Y to X is a PLT blow-up if my morphism mu is an isomorphism outside the closed point X. And moreover, the pre-image of my closed point is an irreducible extensional divisor S. And the pair YS plus the pre-image of delta is T. Lastly, require that the minus my S is an mu ample Q Cartier divisor. So in this case, I call S a Kohler component of my QRT singularity X delta. And if for some positive real number delta, my pair Y S plus the pre-image of delta is delta PLT near Kohler component S, then I call such kind of projective morphism, Bayesian projective morphism mu is the delta PLT block of my QRT singularity. And the advantage of the PLT block is that we can relate a local property of a local singularity X delta to a global one. So in the sense that if we take the adjunction formula for ky plus s plus the pre-image of delta to s, then according to the third property and the fourth property, we got a global log final variety. So we can relate the local property to global one. And by the work of Shortcroft, Prokhoff, Xu, and maybe some other peoples, we know that for any QRT singularity, it always admits a PLT blow-up. And now, somehow we can give an alternative definition of the local volumes. So, or an easy way to compute local volumes. So the work of Li and Xu shows that the local volume is equal to the infimum of the normal volume function, the normal volume of all the possible polar components S over my QRT singularity. So you can see that compared with the original definition of the local volumes, indeed, in order to compute the value of the local volume, we only need to consider a subset of all the possible valuation over X. And yeah, so the definition of the delta PLT block is that under the condition, so I require the first property, the second property, and the fourth property with 3' this condition. Then if mu satisfy all of these 4 properties, then I call mu is a delta-plt block. And for the Nova volume of my color component S, so indeed in Li and Xu's paper, they obtained a formula to compute it. So it is equal to the log difference multiplied with the self-intersection of minus ky plus S plus the pre-image of delta restrict to S. And now let's look at some example to see how to compute the local volume. Indeed, even for a smooth variety or smooth germ, it is not so easy to compute the local volume. So let my S to be the color component of the blow up at the origin point of C to the nth power. Then I can compute the log discrepancy of this divisor valuation, which is equal to n. And in this case, I can also compute the self-intersection of minus ky plus S restrict to S. So by adjunct formula, we know that it is equal to the minus ks to the n minus 1's power, so which is equal to n to the n minus 1's power. So by the formula in my last slide, we know that the local volume of the color component is equal to n to the nth power. And indeed, by the work of Define and Mustata, we can show that this gives the volume minimizer of the local volume at my original point. So this is the first example. And more generally, so we can compute the local volume, or we can give the volume minimizer for any k-semi-stable Q-Fano variety. So let V be a k-semi-stable Q-Fano variety, and I fix a polarization H, so which is an ample Cartier divisor, and I can consider the cone, so which is defined by the spectrum of this guy, and then the volume minimizer is achieved by blowing up at the vertex of my cone. And you can see that from this example, we can see that the some property of the local volume is related to the k-semi-stability theory. And for surface case, so for example, let my AK to be Duval singularities, then I can also compute the local volume, so which is equal to 4 over k plus 1. And in a more general setting, if I let X to be a quotient singularity and G is a finite group, then the local volume of my QRT singularity or the quotient singularity is equal to the n to the nth power over the order of my finite group G. In particular, if I let n equal to 2, so for surface quotient singularity, if I bound the local volume, or if the local volume has a positive lower bound, then from the formula above, I know that I can bound the order of the finite group G, so which is bounded from above by 4 over epsilon. And in this case, indeed, we can show that such kind of singularity are analytically bounded. So in the sense, if I take the completion of this singularity, then it is bounded. So this leads to the following question. So can we say something about the singularities if the local volume has a positive lower bound? So for example, is such kind of singularity bounded in some sense or not? So this is the first question, and I will come back to this question later. Before I discuss more property, discuss our main topic, I would like to introduce more properties of local volumes. So the first property is proved by Liu Xu. So it says that first, the local volume is always positive. So for any QRT singularity, and it has a universal upper bound. So it is bounded from above by n to nth power. Moreover, we can also bound the local volume, bound the MLD of this QRT singularity by local volumes. So the local volume is bounded from above by n to nth power multiplied with the MLD of this QRT singularity. So in particular, if I know the local volume has a positive lower bound, then the MLD of this QRT singularity also has a positive lower bound. Another property that we can relate the global volume with the local volume. So for any Q final variety X, indeed, if I know local volume has an upper bound, then I can deduce that the global volume is also bounded from above. So for this formula, it is proved in Fujita, Liu, Bloom, Johnson's paper. And call that the delta invariant appeared in this inequality characterize whether a Q final variety is K-semi-stable or not. It is shown in Bloom and Johnson's paper that X is K-semi-stable if and only if the delta invariant of X is larger than or equal to 1. And another nice property of volume is the so-called lower semi-continuous and considerable property for local volumes in a bounded family. So to be more precisely, so I let my XD to be a Q-Gronstan family of QRT singularities over a normal base B, and then the local volume function curly X curly D at my close point B. So for this function, which is a function of B in my base, the larger B, it is lower semi-continuous and constrainable in the Zariski topology. So this property leads to a proof of the openness of K-semi-stability in a bounded family or in a Q-Gronstan family of QRT singularities, which is proved by Xu. And for another proof, so it is by Bloom, Liu, and Xu. So now I can introduce one of the main topics in my talk. So there is a folklore conjecture regarding the distribution of local volumes, the so-called ACC conjecture for local volumes. So if I fix the dimension of my variety or the singularities, and I consider all the possible local volumes of n-dimensional QRT singularity, and with the coefficients of the boundary belong to a fixed set I. And then the ACC conjecture for local volumes predicts that if the coefficient set I is finite, then the set of the local volumes is discrete away from 0. And if I satisfy the descending chain condition, then the local volumes, the set of local volumes should satisfy the ascending chain condition. And I think the first part of this conjecture, so which means that the set I is finite and the local volume is discrete away from 0, comes from Liu and Xu's paper. So where they use some property of the gap of the local volumes to conclude that the for cubic threefold the GIT K-stable is equivalent to the GIT is equivalent to K-stable. And so let's recall the ascending chain condition. So this means that for any increasing sequence, A1, which is less than or equal to A2, which is less than or equal to AK, So such kind of increasing sequence stabilizing. So this means that for some very large integer k, ak equal to ak plus 1 equal to ak plus 2, and so on. And so this conjecture, the ACC conjecture for local volume, is parallel to the ACC conjecture for minimal log discrepancies. So recall that the minimal log discrepancy is another invariant to characterize how a singular of a variety is. And it is proved by Shortcroft that two conjectures on the minimal log discrepancies will imply the termination of flips in a minimal model program. So these two conjectures are the ascending chain conjecture and the lower semi-continuity conjecture for minimal log discrepancy. And recall that for lower semi-continuity, for no local volumes, so it is already known. It is proved by Bloom and Liu. And the ACC conjecture for local volumes is still open. And in my joint work with Jihao Liu and Shortcroft last year, so we proved that the ACC conjecture for local volumes is true for example singularities. So I will not define what the example singularity is, but in the ADE classification of surface singularities, example singularities corresponds to E-type singularities, and while D-type singularities are weakly exceptional, and A-type singularities are torrido. So for another result regarding ACC conjecture for local volumes, so in Chen Yang's paper, so if we consider the local volume function in a bounded family of QRT singularities, then the local volume function is constructible. So this result I have already introduced in previous. So in other words, if we can bound both the ambient gem and the boundary divisor delta, then the local volume can only take finitely many values in a bounded family of singularities. So maybe one may ask whether the local volumes belong to a finite set in general, or if under some weak condition, if I can fix the gem X. But however, this is not always the case. So if X is not fixed, then we can see easily that the set of the local volumes is not finite. This is because for surface singularities, for quotient singularity, dual singularity AK, then the local volume can be so AK, the local volume of AK is equal to 4 over K plus 1, so which does not belong to a finite set. And so if I fix the gem X, so suppose that my gem is equal to A2, and I let my boundary divisor to be 1 over 2 Cm, where my divisor Cm is defined by the equation by the polynomial x squared plus y to the mth power. Then in this case, we can show that the local volume is equal to 2 over m, and it tends to 0 when m tends to the infinity. And moreover, in this example, I fix the coefficient sets of my boundary, right? So the coefficient set is equal to 1 over 2, 1/2. And even in this case, so the local volume could tend to 0. So it will not always belong to a finite set. So this example shows that there are some differences if we do not bound the boundary divisor delta. So now I can introduce our main results. So the first theorem I introduced in our talk is about the ACC conjecture for local volumes. So we show that it is true in any of the following situations. So the first situation is that my QRT singularity is Q-Grunstein and it is analytically bounded. So notice that here the boundary divisor delta is not bounded. So the boundary divisor delta may not belong to a bounded family. And the second case is that the dimension of x is equal to 2. And the third case is that the dimension of x is equal to 3, and the boundary divisor is empty, and my singularity is terminal. So the first remark is that here we need to bound the ambient germ analytically, but we allow arbitrary boundary divisor delta. So this is not the same as Schu's result. So in Schu's result, he not only need to bound the ambient germ, but also he need to bound the boundary divisor delta. And in particular, the first case of our theorem shows that the ACC conjecture for local volumes is true when the germ is smooth. Also, another remark is that three-dimensional terminal singularities are not analytically bounded. So even the local volume has a positive lower bound. I think in this case, the terminal singularities, they are not analytically bounded. But by our first case, indeed, and by the classification of terminal singularities, we can reduce the third case to the bounded case. And then we can apply the first case of our theorem. So now let's continue. So let's come back to the question I introduced before. So if I know that the local volume has a positive lower bound, then can we bound the singularities of x? So in general, it is not true, but we can prove that, or we conjecture that such kind of singularity should be bounded in some weak sense. So here is our conjecture. So if we fix eta, which is a positive real number, and I require that the coefficient of the boundary delta, so is bounded below by my positive real number eta, and then we expect that the following two classes of singularities, they are equivalent to each other. So the first class of singularity is the singularity, so which the local volume has a positive lower bound, and the second class of singularity is for QLT singularity. First, I require that the minimal lattice discrepancy has a positive lower bound, and second, I require that such kind of singularities admits a delta-plt block. So we expect that these two classes of singularities, they are equivalent. And if our conjecture holds, then by a result of myself with Jihao, Liu, and Murad, which we use the Bierka BAB theorem. So we show that the singularities satisfy the second condition belongs to a log bounded family up to deformation. So if our conjecture holds, then this implies that for those QLT singularity whose local volume has a positive lower bound, so such kind of singularity is forms a bounded family up to deformation. So it is bounded in some sense. This answers our question. And our second theorem says that, so for the implication from the first to the second, we show that this implication holds in any of the three situations in our theorem 1. So recall that these three situations are first, the QLT singularities are Q-constant and it is analytically bounded. And the second is that the dimension of x is equal to 2. And the last situation is that the dimension of x is equal to 3 and the boundary divisor is empty and x is terminal. So again, under these three situations, we prove that the implication from 1 to 2. And for the converse implication, we show that it always holds. So this is our third theorem. And before before you introduce the proof of or ideas of the proof of our theorem 1, 2, 3, I would like to introduce some applications of our results. So the first application is the boundedness of Cartier index in a bounded family. So if I fix a positive real number epsilon and a log bounded family curly P, then suppose that the set of epsilon log canonical projective pairs x delta belong to log bounded family curly P, then I can show that the Cartier index of any Q Cartier V divisor D on X is bounded from above. And so the Cartier index N only depends on my log bounded family curly P and as well as a positive real number epsilon. So this is the so-called boundedness of Cartier index in a bounded family. So here we have some technical assumption. So for example, here we assume that the set of epsilon log canonical projective pairs. And we expect that maybe this assumption can be replaced by KLT projective pairs. But we need to deal with some technical difficulties. And this corollary actually answers a folklore question. So for example, this question is asked in my journal paper with Liu and Shorkov last year. And there are several non-spatial cases of this corollary. So for example, when X is fixed, it is proved in the paper of Graeber, Kavkaz, Peter Nair, and also proved by my joint work with Chen independently this year. And for another special case is when my V divided D is equal to K plus delta, and which is Q Cartier. Then in this case, it is proved in Bierkat's paper last year. So now I would like to sketch the proof of this corollary. So first, let's make some reduction, or for simplicity, we assume that my right X is always Q factorial, and the boundary divisor delta is empty. So my log bounded family is indeed a bounded family. And now I denote curly X to be this bounded family. And again, so for simplicity, I assume that this family curly X is normal, and the morphism pi from curly X to B is flat, and the whole family curly X is 30. So these are for simplicity, we first made this assumption. And now I can take a base change. So if I let P to be the base change, so I take a base change. First I take the product curly X with curly X over the base B, and I let P to be the base change. And then I consider the fiber over this new morphism in this bounded family, curly X times curly X over B. And I let X to be any closed point in my right X. And I take fiber, then since the base change doesn't change the fiber, so the fiber of curly X times curly X at small x is isomorphic to my right X. So this is because if I take the base change, then the fiber doesn't change. And now I can apply theorem 2 to my new bounded family. And by theorem 2, I know that near the close point X, so for this KLT singularity, it always admits a delta-plt blow-up. And then by my joint work with Jihao Liu and Shorkov, we show that for any KLT singularity, if it admits a delta-plt blow-up, then the local algebraic fundamental group is bounded from above. The order has a universal upper bound. So in particular, the Cartier index of any Q Cartier with divisor D is bounded from above. So we conclude that ND is Cartier near any close point X. And since here I can take all the possible close points of my right X, so I can conclude that ND is Cartier. So this finishes the proof of the first corollary. And here is a remark that indeed my corollary also follows from Xu Zhuang's paper this year, where they prove the so-called the finite degree formula for local volumes. And if you apply this formula and follow some parts of our arguments, then it also implies that the boundedness of Cartier index in a bounded family. So this is an easy corollary of our main results. Okay, so let's see the second corollary. So where we apply our Theorem 2 to the ACC conjecture for minimal lattice frequencies. So again, we fix the dimension of our KLT singularities, and we fix a positive lower bound of our local volume, so which we denote it by epsilon. And I let I be a set which satisfies the descending chain condition. Then in this case, we can conclude that the set of minimal lattice frequency satisfies the ascending chain condition, provides that my gem X is analytically bounded. So recall that for the ascending chain condition conjecture for minimal lattice frequencies, so first it is related to the termination of flips, so which we introduced before. And second, so this conjecture is still open in dimension at least 3, even when my gem X is fixed, but the boundary divisor is not fixed. In this case, this conjecture is still open. And last year, in the same paper of myself with Jihao Liu and Xiaokuo, we proved that if a KLT singularities admits a delta-plt block, then the ACC conjecture for minimal lattice frequency holds. And in particular, we can show that the ACC conjecture for minimal lattice frequency holds for extemporaneous singularities. Since for extemporaneous singularities, we can always show that such kind of singularities admits a delta-plt block. And our strategy to prove the corollary 2 is to use the result I proved with Jihao Liu and Xiaokuo. So indeed, the proof is quite easy. So it is a direct consequence of our Theorem 2. So because by Theorem 2, if the local volume has a positive lower bound and my gem X is analytically bounded, then it tells us that my KLT singularity always admits a delta-plt block. And then by my joint work with Jihao Liu and Xiaokuo, we know that such kind of set of the minimal lattice frequency satisfies the ascending chain condition. And if our conjecture 2 holds, so which means that if we can remove the assumption that X is analytically bounded in our Theorem 2, then together with the work of myself with Jihao Liu and Xiaokuo, we can show that the set of minimal lattice discrepancy satisfies the ascending chain condition, provided that the local volume has a positive lower bound, which means that we can remove the assumption that X is analytically bounded in our second corollary. So these two are two main corollaries of our main results. And now I would like to sketch the proof of our main theorem, so the second theorem. So for simplicity, I already state the first part of our second theorem. So I call it Theorem 2 prime. So theorem 2' says that there exists a positive real number delta, which only depends on fixed positive real number epsilon and eta, such that for any KLT singularities, if the coefficients of the boundary has a positive lower bound eta, and my variety X is Q factorial, and it is analytically bounded, then, and also the local volume has a positive lower bound, then in this case, my KLT singularity always admits a delta-plt blow-up. So this is a statement of our first part of the second theorem. And again, for simplicity, we made some assumptions. So first, for simplicity, we assume that our KLT geom X is fixed, and the coefficient set AI belongs to a rational finite set, and also delta I. So each delta I is a Cartier divisor, and under this assumption, so our next step or our goal is to reduce to the case that when the support of the boundary divisor is bounded, and we will make this reduction in 2 steps. So the first step is that we show an inequality of the log-canonical threshold of X delta with respect to delta and the local volume of KLT singularities. We show that there exists a constant C which only depends on the geom, but not depends on the boundary divisor delta. So if my geom is fixed, then C is a constant. Then C multiplied with the log-canonical threshold of X delta with respect to delta. So it is always larger than or equal to the local volume of our KLT singularities. And this inequality implies that the log-canonical threshold of X delta with respect to delta always has a positive lower bound. And this positive lower bound gamma only depends on my epsilon. So in this case, so this positive real number gamma does not depend on eta. And my second step is that we show that so as I said, that our goal is to reduce to the case that the support of delta is bounded. We want to replace my boundary divisor delta by its case truncation. So by case truncation, I mean that, for example, if my delta is a Cartier divisor F, so if it is a polynomial, then the case truncation of delta is equal to all the terms of F, so whose degree is less than or equal to K. So this means truncation. And we want to show that, so we can take such kind of case conjecture, so where this positive K only depends on epsilon, eta, and gamma, such that the local volume after I taking the case truncation are still the same. And so if I can take such kind of case truncation, then if I want to, for example, if I want to consider the set of the local volumes, then it's fine, right? And moreover, so since if we want to prove the second theorem, then moreover we want to show that there exists some delta-plt blow-up of the singularity after taking the truncation. It still gives a delta-plt blow-up of the KLT singularities of X delta, and we call such kind of delta-plt blow-up a good delta-plt blow-up. And it is worthwhile to mention that it is not always the case that any delta-plt blow-up of the KLT singularity after taking the truncation provides a delta-plt block of the original plt singularities. So we really need to be careful to find such kind of good delta-plt block. And finally, we need to show that the existence of good delta-plt block in a log bounded family. Because after taking the truncation, so since the degree of delta after taking the truncation is bounded from above, so such kind of boundary divisors belongs to a bounded family. So we only need to show the existence of good delta-plt blocks in a log bounded families. And maybe the next step is to give a good or a characterization of what's the so-called good delta-plt block. So as a key observation, we find that if the local volumes of the color components of the delta-plt block has a universal upper bound. So for example, my local volume or the noise volume of my color component is bounded from above by n to the nth power plus 1, then in this case, for any such kind of a delta-plt block, it will gives us a delta-plt block of the original plt singularities. So this is one of our key observation. And indeed, we need to show that for such kind of delta-plt block, we can pull back it and gives a delta-plt block of the original plt singularities. And if we replace the final step, so which says that there exists a good delta-plt block in a log bounded family by Schu's result, which says that the local volumes is a considerable function in a log bounded family, then we can show the theorem 1, so which is about the ascending chain conjecture for the local volumes. Because we can repeat this step, this argument, and since the local volume are the same after taking the truncation, so in order to show the set of local volumes satisfying the ascending chain condition, we only need to consider the set of local volumes of the plt singularities after taking the truncations. So if we follow the same strategy, then we can show the theorem 1. So this is about the ideas in the proof of the theorem 2 prime. And I would like to make some remarks on the proof. So our argument is inspired by generic limit construction from Kohler, Define, and Mustata, and as well as a truncation argument in Schu's paper, which is based on these properties estimates. Which appeared in our proof, and which I made some simple assumption. So the first technical difficulties is that we need to generalize results on local volumes to boundary divisors with real coefficients. So this is because for many results for local volumes, they will already put for boundary divisors with rational coefficients. For example, the result of Bloom, so which says that in the definition of the local volumes, so there always exists a volume minimizer valuation, and indeed can already prove it for boundary divisor of rational coefficients, and also for Schu's results, so which about the constructability of the local volumes in a log bounded families, can already put it for boundary divisors with rational coefficients. And in Schu's results, so can essentially use the so-called the boundedness of monotonic n complements, which is proved by Bierka, appeared in his proof of the Brasov conjecture. And however, the boundedness of monotonic n complements don't hold for boundary divisors with real coefficients. So this caused some technical difficulties, and we need to modify Schu's proof and so that we can conclude that in a log bounded family of TLT singularities with a boundary divisor with real coefficients, the local volumes function is again a conjectural function. And difficulty proof is that our coefficient set is not finite. So for example, in the ascending chain condition of the local volumes, we allow that the coefficient set satisfies the descending chain condition. So it is not necessary to be a finite set. And that difficulty, so we establish a Lipschitz type estimate on local volumes. So by the Lipschitz type estimate, we can reduce the case from the descending chain condition set to the case the finite set, and then we can apply the finiteness of the local volumes in log bounded families to show the discreteness of the local volumes. And the last difficulties arises from that we need to treat analytic boundaries and analytically bounded families, because as I mentioned earlier, so for example, for surface singularities, even if we know the local volumes of surface singularities has a positive lower bound, we could not conclude that this kind of singularities is bounded. So it is only bounded in analytic sense. So in order to show the ascending chain condition conjecture for local volumes holds in dimension 2, as well as the existence of delta-plt blow-up conjecture in dimension 2, we need to treat the and also if we want to show the show both theorems for three-dimensional terminal singularities, again we need to treat analytic boundaries and analytically bounded families. And maybe there's one more remark. If we can prove the both theorems, or especially the first theorem regarding the ascending chain condition conjecture for local volumes holds for three-dimensional canonical Grunstein singularities, then it is possible to prove the conjecture holds in dimension 3 in general for any TLT singularity if we apply the finite degree formula, which is proved by Xu and Zhuang. So these are of three main technical difficulties appeared in our proof. Okay, so in my last slide, I would like to introduce a relation between three classes of singularities which we dealt with in our talk. So the first class of singularity is for those TLT singularities whose local volume has a positive lower bound. And the second class of singularity is that the minimal latitude discrepancy of this TLT singularity has a positive lower bound, and also this TLT singularity admits a delta-plt blow-up. And the third class of singularity consists of those TLT singularities whose minimal latitude discrepancy has a positive lower bound, and also the log canonical threshold of x delta with respect to delta has a positive lower bound. And in our theorem, so our theorem 3 tells us that the third class of singularities belong to the first class of singularities. And our second theorem tells us that if my gem x is analytically bounded, then the first class of singularity belongs to the second class of singularity. And also we conjecture that we can remove the assumption the boundedness of my ambient gem. Again, assume that my X belongs to a bounded family or belongs to an analytic bounded family, then we can show that indeed it is shown in the proof of our second theorem that the first single class of singularities belong to the third class of singularities, and also the third class of singularities belongs to the second class of singularities. And this is our strategy to prove the theorem too. So one of our key observations is to find another class of singularities, and which is very helpful for us to prove theorem 2. This is because it is not so easy to prove theorem 2 directly. So we find such kind of KLT singularities. And it is not always the case that we can remove the assumption that X is analytically bounded. So for example, it is not true that the third class of singularities belong to the second one in general. But for bounded family, this is true. And again, we can also easily find some examples for surface case that the third class of singularities does not belong to the first class of singularities if we remove the assumption on the boundedness. And we conjecture, or maybe we expect that it is always true that the first class of singularities belong to the third class of singularities. And this is a question which we propose in our paper. And also in our paper, we show that the second class of singularities belong to the third class of singularities in general. So without the assumption that X belongs to an analytic bounded family. So the proof follows from the results in our paper and as well as the BAB conjecture. So because using the existence of delta-plt blob, we can relate the global properties about the final varieties with the KLT singularities. So then it is possible for us to prove such kind of results. And yeah, these are all about the relations among the three classes of singularities. And I think I would like to stop here, and thank you for your listening. Thank you very much.
Thank you very much for an excellent talk. Let's thank Jingjun and in the Zoom. Okay, thank you. Thank you very much. Questions, please. Yes. Okay, I have basically questions which we already answered in your talk. So do you now plan to prove conjecture in the full generality in all dimensions, or just treat dimension 3 arbitrary singularities, or what's your next move?
Yeah. Actually, we wish that we could prove the second conjecture, but we feel because the method we developed or we use in our paper, maybe they already worked for bounded families, or maybe I think they already worked for bounded families, and our strategy is that we want to reduce the case that to case X delta belong to a log bounded family. And if without the assumption that X belong to an analytically bounded family, so we don't have any idea. So even for terminus singularities, indeed, we also reduce it to the case that it belongs to an analytic bounded family. So till now, we don't have any good idea to prove this conjecture in full generality. So maybe it is doable for canonical singularity in dimension 3.
I see. Good, thank you. Any questions? More questions? Please ask questions to Jingjun. Okay. Since we don't have more questions, let's thanks Jingjun again. Excellent.
Thank you. Thank you for listening talk.
Thank you. Okay, and on behalf of organizers of Zach seminar, let me wish Merry Christmas to everyone, Happy New Year, and we'll see each other in the next year. But before we stop the seminar, let's make a Zoom picture.
Okay.
Jingjun, do you mind if we close? If you stop sharing?
Okay. Okay. So let me. So poster sharing.
Stop sharing. Stop sharing.
Oh,
So
stop sharing.
Yeah.
Okay.
Oh, yeah. Okay, and I have a gallery view. Okay, let's everyone turn on the cameras. Okay. Paula, hello. Yuri. Okay, Paula's screen is still dark. Okay. Yeah, Paula, okay. We'll wait. Let me practice. Okay, wait. We'll do this in a second. Okay. More. We need more people. Victor. Yuri Gennadьевич, please turn on the camera. Okay. Alessio, Yuji, David, Faye, please turn on the cameras. Okay. Good. We have very nice picture. Okay. Just we wait for more people. Yuri Gennadьевич, hello. Yuri Gennadьевич. Okay, it's nice to see everyone. We have Momo. David, please. Alessio. Oh, wait. Okay. Let me make it big. Okay, we need to. Okay, we just wait a second for two more people. David and Yuri. Yuri Gennadьевич, hello. Yuri Gennadьевич. Yuri Gennadьевич, turn on the camera. Okay. Let me try to make one more Christmas picture and just I count to three. Hi, Fabrizio. Hi. 1, 2, 3. Let me take a look. Okay, it's very nice. Just okay, it's very nice. My son is calling. Okay, I will post the picture somewhere. I'll send. Let me do this. Let me send the picture right now in the chat. Just give me 1 second. I save it here. Desktop. Okay, and let me send it in the chat, and then I'll post it somewhere. Give me 1 second. My computer and desktop. Yes, this one. Okay, picture is uploading. So if you want, you can download the picture from the chat right now. I'll ask Jesus to send it maybe in the next attachment to the next announcement for the seminar. Thank you everyone for participating in this Christmas time of the year and the seminar. Thank you, Jingjun, for the given excellent talk. And it was very nice to see everyone. I think the Zach seminar was very successful in this year. It was nice to see everyone and see each other next year. Our next seminar going to be after 5th of January. 5th of January, no seminar, and 31st of December, no seminar. Happy New Year. Bye, everyone. Happy New Year. Bye. Bye, everyone.